Hello everyone. Today we are going to analyze this propped cantilever beam. In this beam we have the span AB which is 6 meter long, and we have the overhanging part BC which is 2 meter long. In the span AB and in the overhanging portion there is uniformly distributed load 24 kN per meter. From the point B, let us split the beam into two parts, AB and BC. So in the point B, there will be two reactions, RB1 and RB2. To find the moment MB, we have to multiply the uniformly distributed load 24 with the distance and then with the distance by 2. So that for MB we will get 48 kilonewton meter. The uniformly distributed load is acting in the clockwise direction, so the moment MB will be acting in the anti-clockwise direction in BC and will be acting in the clockwise direction in BA. To find RB, we have to add RB1 and RB2. We can easily find RB2 when we multiply the load 24 with the distance 2. We will get RB2 as 48 kilonewton. Now let us take only this part and find RB1. Now let us find the degree of static indeterminacy. In this beam, the number of unknown reactions and moments are 3. The available equilibrium equations are 2. The degree of static indeterminacy will be 3 minus 2. We will get 1. Let us keep RB1 as the redundant. To find RB1, we are going to use strain energy method. We know the formula for the strain energy U, 1 upon 2 EI into integration of m square dx. To use this formula, we have to make sections in this beam. In this beam, there is only one part, that is BA. So we have to make only one section. You can see that I have made a section randomly at a distance of x from the point B. In the integration, the limit is 0 to 6. Now from the point B, we are going to find the moment M. In this case, we have to follow left hand side rule. Clockwise will be negative and anti-clockwise will be positive. RB1 is acting in the anti-clockwise direction, so that it will be positive and the distance is x. The moment 48 is acting in the clockwise direction, so that it will be negative. The uniformly distributed load 24 is also acting in the clockwise direction, so it is also negative. We know that with the uniformly distributed load, we have to multiply the distance and then the distance by 2. X into x, it will be x square. 24 upon 2, it will be 12. We know that when we partially differentiate the strain energy U with respect to RB1, it will be 0. We can only partially differentiate m square because 1 upon 2 EI is constant. When we partially differentiate m square with respect to RB1, we will get this. We can eliminate 2. We can take 1 upon EI on the other side. 0 into EI, it will be 0. Let us apply m. Let us partially differentiate m with respect to RB1. In this term, for RB1, it will be 1. In these two terms, there is no RB1. So the differentiation will be 0. 1 into x, it will be x. Let us apply that. Let us multiply this with the x so that we will get this. Then using the formula, we can do the integration. After integrating and simplifying, for RB1, we will get 66. Now using the rule sigma v is equal to 0, we can find RA. Let us take moment about A and find MA. RB1 is acting in the anticlockwise direction so that it will be positive, and the distance is 6. So 66 into 6. The moment 48 is acting in the clockwise direction, so that it will be negative. The uniformly distributed load is acting in the clockwise direction, so that it will be negative. We know that with the UDL we have to multiply the distance and then the distance by 2. Let us assume that MA is acting in the anti-clockwise direction, so that it will be positive. Finally, for MA, we will get a positive value. That means our assumption is correct. Now let us consider the overhanging part also. To find RB, we have to add RB1 and RB2, so that we will get 114 kilonewton. Then using the right hand side rule, we can find the shear force values. Here you can see the shear force diagram. In this point, the shear force becomes 0. In this point, there will be maximum positive bending moment. Let us make a section in this point and find the distance. You can see that in that point, I have made a section at a distance of x from the point A. We know that in this section, the shear force is 0. Using that concept, we can find x. Now let us find the maximum positive bending moment. We can use right hand side rule. MA is acting in the anti-clockwise direction, so that it will be negative. RA is acting in the clockwise direction, so that it will be positive, and the distance is 3.25. The uniformly distributed load is acting in the anti-clockwise direction, so that it will be negative. We know that with the UDL we have to multiply the distance and then the distance by 2. For the maximum positive bending moment, we will get 42.75. Let us find the bending moment in the point A. In the point A, we have MA, which is acting in the anti-clockwise direction, so that it will be negative. To find the bending moment in the point B, we can use left-hand side rule. The uniformly distributed load 24 is acting in the clockwise direction, so that it will be negative. We know that with this load we have to multiply the distance and then the distance by 2. For the bending moment at B, we will get minus 48. We have already found it before. Here you can see the bending moment diagram. In these 2 points, the bending moment becomes 0. These are the point of contraflexures. We can make sections in the beam and find the distances. In those 2 points, I have made sections at a distance of x from the point A. Now, using the right hand side rule, we can find the moment, which is 0. Then we will get this equation. Then using the calculator, we can find the values of x. This x is 1.362 and this x is 5.137. Now we are going to end this session. Thank you for watching this video.